So welcome back to my lectures on Galois theory. Our next topic is separable extensions. Our basic goal of Galois theory, as I stated earlier, is to study the structure of algebraic extensions using automorphisms. This is our basic goal in Galois theory. So, to do that, we have defined a lot of properties of field extensions, and some of them are this: the degree of an extension, that is E over F. If E is a finite extension of F, this is the number of elements in the basis when E is considered as a vector space over F. And we also defined the group of automorphisms. The group of automorphisms. And that is G or F. This is actually the number of, this is the group of automorphisms on E leaving F fixed. Our goal is to find out the conditions on the extension E. E is an extension of F, right? Extension of E such that this number is equal to the order of this. That is, E over F is equal to the order of G over F. This is our goal. Once you establish this one, we know that that is the extension we are looking for in Galois theory. And towards this end, we already defined a property of this extension is called splitting field. So we thought that if Q of root 2, if this is our E and our F is equal to Q, then E over F is equal to 2, and that is equal to the group of automorphisms, the order of the group of automorphisms. This is because E is the splitting field over Q or F. Over here you can say this is Q of root 2 is over Q. That is because the roots or the zeros of the reducible polynomial of root 2, all the roots are in E. And we have another counter example on this. If you say A equal to Q of cube root of 2 and F is equal to Q, then E over F is equal to 3, whereas the group has got only one automorphism. And that is because E is not a splitting field. The irreducible polynomial x cube minus 3 minus x cube minus 2, the zeros of this x cube minus 2 is not, all zeros are not in E, only one of them is in E. So one way to make these two are equal is to make sure that E is a splitting field. But if E is a splitting field, can we always say that these two numbers will match? And that is where the idea of separable extension comes in. Actually, if you just say it's a splitting field, that is not sufficient enough to say that the degree is going to match with the order of automorphisms, group of automorphisms. Because if the irreducible polynomial of alpha over f, alpha belongs to E, here the irreducible polynomial of root 2 over q is equal to x square minus 2. So the zeros are root 2 comma minus root 2. They are distinct. But if you have same roots, if an irreducible polynomial has zeros with multiple occurrences, meaning this will be something like x minus alpha whole square. Like here, it will be something like the irreducible polynomial of alpha is equal to x minus alpha to the power of 2 or 3 or something greater than 1. So something like this. If the irreducible polynomial of this form, then even if alpha belongs or alpha and other zeros of this polynomial belongs to E, that means even if E is a splitting field, these two numbers will not match. Now, the question is, do we have such irreducible polynomial? If we can prove that there is absolutely no irreducible polynomial with zeros of multiple occurrences, then we don't need to look for another condition. Or another condition on this extension so that this can be equal. So our next aim is to find an extension of a field such that an irreducible polynomial has roots with multiple occurrences. If we can show one example, that means we need to consider something else. So some other conditions on E, and that is where the separable extensions comes in. Let us start with a definition. Let f of x belongs to f of x. Then alpha is a 0 of f of x with multiplicity v if x minus alpha to the power of v is a factor of if v is the highest integer such that x minus alpha to the power of v is a factor of f of x. Example is, let's take f of x equal to x cube minus 3x square plus 3x minus 1. Here x minus 1 is a factor. X minus 1 is a factor of f of x. Divides f of x. X minus 1 whole square also divides f of x. X minus 1 whole cube also divides f of x. And x minus 1, 4 does not divide f of x. So the multiplicity is 3. That's what I meant here. You may have a polynomial with a lesser degree, but that's not what you are looking for. So our next aim is to find a field and an extension such that there exists an irreducible polynomial f of x in f of x. This is irreducible such that it has a 0 with the multiplicity greater than. That is the reason for defining the separable extensions. So let's start with I'm not going to the details of the proof of this example. I'm going to outline how we are going to do this because that is not our focus. So let us start with ZP. ZP is a finite field of P elements 0, 1, P minus 1, where P is a prime number. I'm going to assume that P is a prime number greater than 2. Now I'm going to define another field here, ZP of y. This is not ZP of square bracket y. This is actually curly bracket. This is a field of quotients of polynomials in y over ZP. The elements will be like something like 4y square plus 3y plus 1 divided by 3y minus 1. This is the kind of elements you will have it here. So definitely, and this is a field, definitely this is a extension of ZP, because ZP is considered as a field of constant polynomials. And in between these two, I'm going to define another field. In this field, here the indeterminate is y. So any power of y comes in here. Here, the indeterminate is y to the power of p. So you'll have polynomials like 3y to the power of 2p plus 2yp plus 1 by 3y to the power of p plus 1. Something like that. So this is actually definitely a subfield of this. The first claim is this is going to be our f and this is going to be our e. The claim is ZP of y is a finite extension of ZP of y to the power of p. Not going to do the proof of this, verify. In fact, the basis of the vector space VP over y, ZP of y over ZP of our y square y to the power of p is 1 y dash dash p minus 1. That is why it's a finite extension, and the degree of z to the power z of y over zp of yp is equal to p. Now consider a polynomial f of x equal to x to the power of p minus y to the power of p. So clearly y is a 0 of x to the power 0 of f of x. Actually, y does not contain here. Y is somewhere here. So if you take the diagram here, this is our ZP and this is our ZP of YP, and this is our ZP of y. So y is somewhere here. It cannot be here. This is a 0 of f of x. And the irreducible polynomial of y over ZP of yp is actually f of x. That is because this is the polynomial of lowest degree where y is a 0 of f of x. This is a polynomial. This is a polynomial in where I need to write that 0 of f of x, and that belongs to ZP of y to the power of p of x. In here, the lowest degree of the indeterminate is p. Right? So this is the smallest. You cannot, if you reduce to a lower degree, that will not belong here. So that is why this is the irreducible polynomial of y. And also the degree of ZP over y over CP of our p is p. So f of x is an irreducible polynomial. But x to the power of p minus y to the power of p is equal to x minus y to the power of p. If you expand this one, you will have binomial expansion. All the terms except these two will have a p there. And if there is a p, that will be automatically become 0 because this is of characteristics p. So this implies y is a 0 of f of x with multiplicity equal to p, and p is greater than 2. So we found an irreducible polynomial with 0 having multiplicity more than 1. And that is what we are looking for. We'll have a theorem here. If f of x belongs to f of x is an irreducible polynomial, or f or f of x, then all the zeros of f of x have the same multiplicity. Meaning if alpha is a 0 of f of x with a multiplicity v, then beta, if there is another 0 of f of x, then its multiplicity is also V. So, proof. Let alpha and beta are zeros of f of x. Then there exists a conjugate isomorphism from f of alpha to f of beta such that f of alpha such that psi of alpha of is equal to beta. So that is like something like this. F here, and you have an F closure here, the alpha here and beta here, and this will be, or f of alpha, and this will be f of beta, and this is our psi of alpha beta. Now, this is an isomorphism. So this psi of alpha beta can be extended to a toe from F closure to F closure. Now we are going to construct another isomorphism. Going to take this out here. T to toe is actually from F closure to F closure. Now you are creating another isomorphism Tx from f of x to f of x by, see what are the elements here? Constant polynomials and polynomials with x. So we need to define both. So Tx of alpha or A is equal to tau of A for all A in F. That is a constant polynomial. And another one is the polynomial, the non-constant polynomial that is generated by x is equal to x. So for example, the Tx of 3x square plus 2x plus 1 is equal to T of 3x square plus T of 2 plus x plus 1. But this is, the tau is an extension of psi alpha beta. And what does psi alpha beta do? Psi alpha beta is an isomorphism from f alpha to f beta, leaving f fixed. Meaning, this is actually 3. Because this goes to, this is actually, this will be equal to psi of alpha beta of 3 x square plus psi of alpha beta 2 x plus 1, and this is equal to 3x square plus 2x plus 1. That is how we define this isomorphism. Meaning, so you can say, so tau can induce an isomorphism Tx from f to f of x by T of x of a is equal to a for a in f, and Tx of x is equal to x. Once you define this, this means that Tx of f of x is equal to f of x. It is not going to move f of x because f of x contains coefficients from f and x. It's a polynomial, and the coefficient is not going to move because coefficient, this is from f, and c of alpha beta of a constant is the same thing. So it is not going to move, it's not going to change. Now Tx of x minus alpha to the power of v will be equal to x minus beta to the power of v. Because of this, you expand this using binomial theorem, and wherever you have an alpha, replace alpha with beta. All others will be same because of this. So this means, so if this is a factor of f of x, then this is also a factor of f of x. So if v is the multiplicity of f of x, then the multiplicity of beta, if v is a multiplicity of alpha, or multiplicity of alpha, if v is a multiplicity of alpha in f of x, then the multiplicity of beta in f of x is greater than that of alpha, because of this. See, if this is the multiplicity of, if v is the multiplicity of alpha, meaning this is a factor of f of x, then this is a factor of f of x. This is a factor of x of x doesn't mean that you cannot have x minus beta plus 1, v plus 1, a factor of this. So that is why I am saying the multiplicity of beta in f of x is greater than or equal to that of alpha. So similarly, we can prove that the multiplicity of alpha is greater than or equal to the multiplicity of beta. And that implies the multiplicity of alpha and beta are. Now we'll have one more theorem. Let f of x belongs to f of x be an irreducible polynomial. Then f of x has a factorization of the form f of x equal to x minus alpha I to the power of v, where alpha i's are the zeros of f of x with the multiplicity It's a very straightforward result from the previous result. So if alpha i's are the zeros of f of x with the multiplicity v, then x minus alpha i's to the power of v are factors of f of x. And there cannot be any other factors. Or there cannot be any factors other than alpha i's. So that implies f of x equal to pi of I x minus alpha I to the power of v. See, we have a same v for all the zeros, same multiplicity for all the zeros.